Hello. Today I'm going to be sharing with you our group's efforts to understand the mechanism of ethylene polymerization using D8 metal atoms supported in zeolites. Ethylene polymerization is of interest due to its use as a feedstock for a number of commodities. For example, it impacts industries such as plastics, petrochemicals, and rubbers. The schematic at the bottom outlines a skeleton of how ethene can be used to produce a number of chemical species. For example, ethene can be dimerized to form butenes, which can be further polymerized to form longer chain alkenes and alkanes through hydrogenation. Butene and ethene can react with each other to form hexenes, and the subsequent cyclization of the hexene can form aromatics. You can also form propene through metathesis. The increasing use of shale gas over naphtha in recent years could potentially lead to a larger supply of ethene, and that has renewed interest in studying this reaction. The first example reported for nickel catalyzing the polymerization of ethene was reported by Carl Ziegler's group. In trying to study the Aufbau reaction in which ethene is reacting with triethyl ammonium, they observed the formation of butenes, which was attributed to trace amounts of nickel salts being present in their system. Since then, the process has been scaled up to the industrial level, where a few examples of homogeneous nickel-based organometallic catalysts are used to produce or to catalyze ethylene polymerization. However, there's not presently a heterogeneous analog at the industrial scale, which has really fostered interest in developing such a process and understanding how it works. A number of studies have looked at this chemistry. Oftentimes it's speculated that it takes place via a Citation mechanism, whereby your nickel hydride species interacts with ethene through a series of surface interactions and changes. It interacts with another ethene to form butene and restore the nickel hydride species originally present. However, the true intermediates present during this reaction are not known, and oftentimes the identification of the active site is not clear, at least not clear under operating conditions. There are some further uncertainties in the mechanism, where it's been noted that the presence of hydrogen increases the polymerization rate, as has been reported for supported rhodium materials. However, it's not clear how the polymerization is taking place in the absence of metal hydride species, seeing as how important that metal hydride was for the Citation mechanism. Further, the understanding this is complicated by a diverse pool of catalyst materials that have been reported in the literature. So, for example, nickel, I have outlined 7 different species that have been proposed at one point or another. As you can see, a number of different species can be present on the surface. So you can have isolated nickel OH species, dimers, isolated nickel 2+, nickel oxide, etc. And sometimes the catalyst surface will have a mixture of these types of nickel species. So our first strategy in trying to understand this mechanism is to develop well-defined single species catalysts for which to probe this reaction. If we try to synthesize the dispersed nickel species on an H form of zeolite to exchange the cation, which is balancing the aluminum center, we get competition between the protons and the metal ions, which results in a material with low dispersion. And if we try the aqueous method, we also have a propensity to form these nickel OH nickel interactions, which are precursors to nickel oxide formation on the surface, which is also undesirable in our aim to form a uniform metal site at a dispersion which we can then more easily spectroscopically probe. And so our strategy was taken from emissions controls in synthesizing these materials, whereby we use a nickel nitrate salt dissolved in ammonium hydroxide, which forms ammonium as the charge balancing cation in the zeolite framework. And through a thermal treatment, we are able to decompose the ammonium nitrate to form N2O and H2O, leaving behind isolated nickel 2+ atoms on the surface of the zeolite. We characterize these materials with infrared spectroscopy, CO adsorption, and what we see is a nice, pretty clean spectrum of CO on nickel at 2211 here, suggesting to us that we are forming uniform and atomically dispersed sites. This peak at 2162 is from the C13 isotope. We can also look at the STEM imaging to observe our dispersion, or at least the potential presence of nickel clusters on the zeolite, and its absence further supports our notion that these are indeed isolated nickel 2+ species in the zeolite. With our material characterized as a well-defined nickel 2+ species in the zeolite, we proceeded with testing it for the dimerization of ethylene. So here is our reaction results for 0.4 weight percent nickel supported on beta zeolite. And what we can see is that even at 80 degrees, we are noting activity, which increases at higher temperatures, accompanied by deactivation. And we have initial turnover frequencies of butene ranging from 12 to 400 per hour. Notably, we're also observing the formation of butadiene through the dehydrogenative coupling of ethylene. And those selectivities range from about 30 to 60% depending on the reaction conditions. It should be noted that the production of butadiene from ethene on supported metal, zeolite supported metals, has been previously shown for rhodium system by Kavantsev in his dissertation. Characterizing the material after a reaction shows that our nickel 2+ center has diminished availability to the CO after catalysis. So that peak is much smaller, but we also do not see any reduction or features that would indicate a reduction to nickel 1 or nickel 0. We do, however, see some formation of extra framework aluminum and CO's ability to bind with that here at about 2230. If we look at the carbon NMR, either through cross-polarization or single pulse sequence, we can see that a number of unsaturated hydrocarbons are present on the surface and that they are likely blocking the active centers, which has led to the deactivation we observed. We also prepared a supported iridium catalyst, in this case 0.7 weight percent iridium dicarbonyl on phagosite, and tested it for its activity in ethene dimerization. As you can see from the table, at low temperatures, it had lower turnover frequencies of about 1.5 to 20 turnovers per hour over the range of 80 to 180 degrees C. And the products formed were exclusively butenes. However, when we increased the temperature to 225 degrees and tested this material, we saw about an order of magnitude higher in turnover frequencies, as well as the formation of butadiene at a selectivity of about 30%. Characterizing this material with infrared, we can see that the fresh catalyst exhibits clean features indicative of iridium dicarbonyl, where we can see asymmetric and symmetric stretching at 2038 and 2108 wave numbers respectively. And interacting this species with ethene gives us the displacement of one of these carbonyls, so the dicarbonyl features dissipate, and we see a feature indicative of iridium CO ethene form right here, which shows us that ethene is indeed able to displace carbonyl on this catalyst readily. If we look at the STEM images of this material, the fresh images on the left-hand side show us that iridium atoms are neatly and isolatedly placed in the supercages of the phlogisite, and that after reacting in our test unit for an hour, we don't see any agglomeration of those iridium centers. What we do see, though, over the course of reaction is some changes to the framework overall. So this scale is about 100 nanometers, and we can see that these crystals fractured. It kind of looks like little tunnels present in these STEM images. And having established that these materials are indeed active for ethylene dimerization and that they are well defined, the question turns into how are they undergoing these transitions. And so for that, we turn to infrared spectroscopy to try and tease out the mechanism taking place here. And what we have is a test whereby we took the iridium dicarbonyl catalyst and exposed it to ethene in the transmission cell and observe what changes were taking place to the spectrum. And so we're going to start with just an expanded segment of this series here on the right-hand side, or the left-hand side, whereby we see the initial formation and decrease of, very quick formation and the decrease of features at 2053 wave number and 2066 wave number, which is this iridium dicarbonyl, which is interacting with an ethylene, which dissipate and give rise to this peak at 2056, which we ascribe to a square planar iridium carbonyl ethylene fragment. Meanwhile, what we also see occurring is the increase in features at 2112 and 2178, which we ascribe to an iridium carbonyl vinyl hydride species. And these reach their maximum at after about a minute before decreasing. And we'll note that the CO stretch is notably higher in wave number, and so we ascribe that to be due to the oxidation state of iridium transferring to +3. And after that, or as that declines, we see the rise of a peak at 2087, which we ascribe to this fragment, whereby another ethylene is now interacting with the iridium atom. Notably, this fragment does not exhibit any iridium H stretch, which supports our notion of this transition taking place. But we also have some additional spectroscopic evidence to support that, whereby we use deuterated ethylene, which is the spectrum shown in blue. And so these two spectrum are the same experiment, just with a different isotope of hydrogen in the ethylene. So what we can see is the spectra look largely the same, with the biggest difference being that we no longer can observe an iridium H stretch when we're using deuterated ethylene. So that confirms our previous assignment. We can also use NMR, so we use in situ NMR to try and support the observations by infrared. And what we can get from this, cross polarization and single pulse, are, of course, ethene gas here, or at least molecular ethene, as well as pi-coordinated ethene and vinyl fragments, if we increase the scale by 25 times, which is what the green is. So that supports our observations by infrared as well. And taking all of this together, we can propose a mechanism. It's shown here for iridium, but we propose that an analogous mechanism can be drawn for nickel 2+. It's just we will have the absence of the carbonyl species present. So the first step after adsorbing an ethene and displacing one of the carbonyls would be oxidative addition to form this iridium hydride. the second ethene comes in. We showed this fragment taking place. And this is kind of where the mechanism branches. It could be that the vinyl migration takes place, followed by a beta hydride elimination to form butadiene, which we do see at higher temperatures on the iridium, and at the probe temperatures on the nickel. We could also form butene in this direction, either by reductive elimination or through an ethyl migration, followed by a beta hydride elimination. But all of them will restore our catalyst to a state in which it can continue to catalyze this reaction. So in taking what we've learned from our iridium and nickel systems and the mechanism that we proposed for them, we thought that this could have implications on the mechanism for the Phillips catalyst, chromium supported on silica, which is believed to follow the Closey-Arlen mechanism. It's been challenging to really clarify this mechanism for several factors which are listed here, namely low number of active sites, the amorphous nature of the silica, fast reaction rates, and the presence of multiple chromium oxidation states that have really made it challenging to tease out the initiation mechanism. In the absence of hydrogen, where do we get this hydride species? So applying what we have discovered for our own system, we have proposed this scheme for which chromium is catalyzing ethylene dimerization. So similar to what we saw or showed before, ethylene can interact with the metal site to form the vinyl hydride species. We get the ethyl formation after another ethylene interacts with that hydride. And then at this point, we can have chain growth events to form longer carbon chains and eliminate our alkenes via either reductive elimination or a beta hydride elimination. So that just kind of proposes how a Phillips catalyst might operate. In conclusion, I guess I would like to just summarize that ethylene dimerization is occurring on our D8 metal cations that are supported in zeolites, and we do this in the absence of an initial hydride. So the hydride is forming during the reaction via homolytic activation of ethylene CH bond, which we note is stronger than methane, on electrophilic iridium centers in the zeolite micropore. And that both the iridium and the nickel can produce not only butene, but butadiene under mild reaction conditions. And so with that, we would like to acknowledge several entities, notably the Department of Energy and PNNL for financial support, EMSL, which is the user facility for which we conducted these experiments, university that we're affiliated with and collaborated with, as well as the ARCHE Foundation. And then special acknowledgments to Dan Klass, who was instrumental in being able to conduct these experiments, as well as the LDRD funding that we achieved through Quickstarter for this project.